Hello, everyone. Can you hear me? Okay. So, folks, I am denying requests to for Otter because I've found that anytime I let people record, Zoom's own recording fails, and so we've had at least one lecture where the entire lecture recording just vanished. So you'll have to pardon me for it. There will be no permission for auto recordings, number one. Number two, again, as always for the Zoom lectures, there is no attendance poll. Please don't ask. We get the statistics also. Okay. All right, let me begin. Can someone remind me what the last topic was that we covered? Anybody? What was the last topic we covered? CTC, right? Exactly. And we were talking about sequence-to-sequence models. So sequence-to-sequence models are problems where you have a network which takes as input an entire sequence, some x1 through xn, and outputs a sequence as opposed to taking a single input and generating a single output. For example, speech recognition. Speech goes in, a word sequence comes out. Or machine translation. An English word sequence goes in, maybe a German word sequence comes out. Or dialogue systems. Your user statement goes in, the system response comes out. Things like that. In general, in all of these, the length of the input sequence may have nothing at all to do with the length of the output sequence. So we saw one specific case of sequence-to-sequence modeling in the last class, where what was special about the kind of sequences we discussed in the last class? Can someone remind me? What was special about that? About the sequence-to-sequence model? The problem, anybody? We made an assumption about the alignment, right? And so what was the assumption we made about the alignment? Can you remind me? Somebody. Did we assume the input and output were aligned in some manner in these problems? It had to be order aligned, right? So although the number of outputs was not the same as the number of inputs, there was an order alignment. So that's what we dealt with. But more generally, you cannot assume any such thing. For example, if I'm translating a language, if I translate English to, say, German, I eat an apple goes in. One translation could be Ich habe einen Apfel gegessen. And then if you begin looking at the correspondence, there is no one-to-one correspondence between the input and output. There is no order correspondence. A single input, like eat over here, could become multiple outputs. Habe gegessen. And something that occurs early in the input over here, eat, could end up at the end at the output. Or even these extreme cases like a dialogue system where you say my screen is blank, and the system comes back with, can you check if your computer is plugged in? And there's no apparent relationship, no apparent correspondence between the input and output at all. So this is the kind of model that we're going to be dealing with. But before we get into that, we're going to talk about language modeling. Here's a nice little example. This was very popular on the web for a while. It looks like a beautiful piece of C code, right? So can anybody guess where this came from? Anyone? Just a guess. I guess nobody wants to hazard a guess. But this was just, yeah, it looks like the Linux kernel, right? It was just a recurrent neural network that was trained on Linux kernel code and made to run in generative mode. And look at how beautifully it's generated outputs. It looks exactly like C code. This would compile. It needed some cleanup, but for every open parenthesis, there's a corresponding closed parenthesis. The loops are perfectly cogent. So here, for example, for I equals 0, I less than blocks, I plus plus is the same variable that's being tested or incremented. And within the code itself, that same variable is also being used. And every open curly brace is being closed. It looks like something a human being might have written because it's so clean. but it wasn't. Or here's a text page with math in it, very complete with figures and theorems and lemmas. Again, it's not as something as fancy as ChatGPT might produce, but it's actually very plausible. And this is an ancient piece of work, right? Or here's a Wikipedia page. This was a recurrent neural net. This was a recurrent neural network trained on LaTeX from lots and lots of papers. This was a recurrent neural network trained on Wikipedia pages and then made to generate stuff. And it comes out with naturalism and decision for the majority of Arab countries capitalized, was grounded by the Irish language. It's nonsense, but it looks completely, English, right? So what kind of model could generate something like that? It may not look very impressive at first sight, but then these are examples generated by Andrei Karpathy in 2015, and it's a simple 3-layer LSTM that was trained and run in generation mode, and amazingly it generates this totally cogent text. Of course, these days you have ChatGPT, which is a lot more complex, but it builds on the same idea. And what we're going to do over the next few classes is to see how we can build up from this simple recurrent neural network, which can do stuff, to something more fancy like ChatGPT. So what all of these models are doing is modeling language. And so we're going to spend the next few minutes talking about modeling language using recurrent networks, and more generally about language models and embeddings. So if I asked you to tell me what language modeling was, how would you answer me? What is your definition of language modeling? What is language modeling? Can somebody tell me? What does a language model do? Maybe you can tell me that. Next word predictor, that's a good answer. Something better than that? Generates first words conditioned on previous words. A language model literally models language. That's all it does. It models the statistics of language. So if I were to give you a word sequence like, modeling language using recurrent neural networks, what a language model can do is somehow characterize the probability distribution of the language and tell me what is the probability that this word sequence could have been randomly produced. That making sense to you guys? It's not about next or word prediction. It's not about generating stuff. It's literally just giving you modeling the probability distribution of word strings in the language. Is that making sense? Yes, no. Everything we do is going to build on that, right? So amazingly enough, that's all we really do. So language models model the probability distribution of token sequences, where tokens could be words. If the tokens, if the tokens are words, they are modeling the probability distribution of word sequences. Once you have that model, you can do various things like compute the probability of a given token sequence or generate sequences from the distribution of the language. But really, what you're actually doing is constructing a model which can compute this for any word sequence. This is what a language model learns to guess. Is that making sense? Yes, no? I see one yes. What about the rest of you? So I'd like to see, if a dozen at least, so I know that, some of you at least got it. So 7. Okay, the numbers are weak. Please be a little more prompt so I know I'm not losing you in the coming slides. Okay, so where does this, if what we are doing is modeling this, where does next token or next word prediction fit in? Because that's how you are familiar with language modeling, right? That's what you think language modeling is all about. Now consider this word sequence. What is the probability of this word sequence? Using Bayes' rule, I can write it as the probability of word 1 times the probability of word 2 given word 1 times the probability of word 3 given word 1 and word 2, and so on. So I'm decomposing it, where at each step, I'm computing the probability of one word, basically the next word, given the entire word sequence, right? So, and this is why we think of it as next token or next word prediction. Given everything before, you're always predicting the next word. But the point of this is that by chaining these up, you can actually compute this, and this is a much more challenging task than this guy, because there is an infinity of word sequences, whereas if you have to predict only one word, the set of possible options is much smaller. So is this making sense? That next token or next word prediction is actually a tool. But what we are really doing is computing this guy, right? So everyone go to this. Give me some thumbs up, guys. If I see 50 of them, I'll move on, because this is important. There are like 170 people in class. I should be able to get 50 thumbs ups, right? It's 32. This is hard, like 1/5 of the class. Hopefully the next time I ask this question, that number will be greater, okay? So again, language models actually model the probability distribution of entire sequences. They could model the probability distribution of sentences. What is the probability of this paragraph? What is the probability that a completely random sample from the language will produce Les Miserables, right? They model language. But then we model it by modeling, always trying to compute the next token at a time, at each time, because this we can't deal with the more complex problem of modeling entire sequences. It's much simpler to model the probability of the next token. So given that, this is what we sort of reduce the language modeling problem to. If you see 4 score in 7 years, what do you think the next word is? Anyone? What do you think the next word is over here? Over here, if you just saw 4 score in 7 years, what is the next word likely to be? Ago, right? So where did you learn that? Why do you think it was ago? Somebody? Why did you think it was ago? Abraham Lincoln's speech? Because 4 score and 7 years ago is a very famous sentence in the English language. So it's such a strong pattern that if you see any portion of it, the rest is implicit, which is why you predicted ago, right? Similarly, Abraham, if I ask you what the next character is, you're almost going to tell me N, right? So Aditi, that's because of this. I'm using Bayes' rule to decompose the probability of the entire sequence to always predicting the probability of the next token. Did that answer your question? Because this is PW1 times PW2 given W1, right? And so on. So we can focus on that, okay? But again, always remember that it's the probability of the entire word sequence, okay? So how can I do this? Computationally. First, I'm going to represent all my words as one-hot vectors. I pre-specify a vocabulary of n words in some fixed order, say lexical order, and then we know exactly how to convert every word in it into a one-hot vector where the vector is the same length as your vocabulary. All entries except 1 are 0, and the one entry that is not 0 has a value 1, and that is the index corresponding to the word you're trying to represent in your lexically ordered sequence of words. If you are modeling characters instead of words, then your vocabulary would consist of characters. English will require about 100 characters to include both cases and punctuation and such like. You would again arrange them in some order, and then any single character gets converted to a one-hot vector. Now, there's nothing particularly fancy about this. Again, is this familiar to all of you guys? Yes or no? Right? This is clear, right? So, and so now, if I'm speaking of the next word prediction, what is this problem here? given the previous n minus 1 words, I'm trying to predict Wn. So in other words, I want to compute some function Wn that equals f of W1 through Wn minus 1. So this is what the next token or next word prediction problem is. And I'm using that to actually model the probability distribution of entire word sequences. And so we need this guy. And how can we build a model? This is what it's going to look like. We're saying Wn is some function of the previous n minus 1 words, or W0 through Wn minus 1 words. So the n plus 1th word is some function of the previous n words. If I were to write it in, in some, if I were to sort of show it pictorially, you have this block f, which is the function, which takes all of your previous n words, each of those represented as a one hot vector, and then outputs a one hot vector, which represents the next word. And if you can train this model, then once you feed it a set of words, it's going to be able to predict the next word. And you can train it using regular backpropagation if this is a neural network. Now, there's a problem over here. You're using one hot representations for everything. And the problem there are two problems with one hot representations. But the primary one is dimensionality. If I have a vocabulary of say 100,000 words, then how many dimensions is each one of these one hot representations? How many dimensions is it? 100K, right? That's a gross abuse of dimensionality. And so to get an idea, right, take a look at this. If I have 3 words in my vocabulary, then I'm actually using a 3-dimensional space, but in the 3-dimensional space, the only points I'm using are these 3 guys. 1, 0, 0, representing the first word in the vocabulary. 0, 1, 0, representing the second word in the vocabulary. 0, 0, 1, representing the third word in the vocabulary. If I have 100,000 words in my vocabulary, then I have 100,000 dimensional space, right? I mean, I can't draw 100,000 dimensional space. And yet, in this vast 100,000 dimensional space, I'm using only 100,000 points. Is that an effective use of the space? Would you call this an effective use of the space? No. So why are we using this? Why are we using a one-hot representation? Anyone? Why do we use it? Any guess? Can someone suggest why we would use a one-hot representation? No assumptions, maximum detail. Can you expand on that? What do you mean by no assumptions? Orthogonality. So here's what it is, right? If I used any other kind of representation, then if I look at the distances between words in this vector representation, some words would be closer than others, which means you're assuming some kind of a relationship, distance relationship between words. Whereas if I use a one-hot representation, what is the distance between any two words? What's the distance between any two words? What's the distance over here if I'm using a one-hot representation? Anyone? Well, it's always square root of 2, right? For every one of them, it's square root of 2, which means that you are not making any assumptions about which words are close and which words are distant. You're being perfectly agnostic and you're letting the system learn without imposing your own assumptions on these words. That's why we use one-hot representations. But then this is a terribly wasteful use of space, right? For one thing, 001 is a word, but if I take 001 plus epsilon just slightly off, that doesn't mean anything. There's no word, right? Also, if I take a unit volume and see how many points there are within that unit volume, the density, that's going to be very, very low, right? It's order of n over r raised to n, if r is the size length of the edge. I have for n words, the actual volume of this cube is r raised to n. This is the cube on which we're using some corners, right? So it's a tremendously inefficient use of dimensions. So again, is this picture making sense? This is for the 3-word vocabulary. And all the words just live on these corners, these three corners, right? So instead of just using this, what we will do is propose a lower dimensional hyperplane and then project every one of the points onto this hyperplane. And the projection operation is very simple. We know it's just multiplying by a matrix P. And we discover this hyperplane. And if you let this, and discovering the hyperplane is the same as discovering this projection matrix P. And so this P, if I have 100,000 dimensional vocabulary, then these are all, every vector is going to be 100K. This hyperplane could be, say, 20 dimensions or 200 dimensions, which means I'm projecting everything down onto this 200 dimensional hyperplane. What would the size of P be if I have 100,000 word vocabulary and my hyperplane is 200 dimensions? What will the size of P be? Anyone? What will it be? It's going to be 200 cross 100K, right? So you manage to, and that's how you bring the dimensionality down. And so if you learn this properly, then once you project them, the distances between the projected points can hopefully actually capture the semantic relationships between words. So how do we implement this? Every word is now going to be replaced not by the one, you're not going to use the one hot representation, but you're going to use the P times the one hot representation. So every one hot representation is going to be followed by this matrix P, and that's what goes into the function. And the output, of course, is predicting a word, not the actual one hot representation of the word. And now you can use backpropagation to learn everything, including this function and this P. Now we know that a matrix multiply is just a simple linear layer, right? So this whole thing, if F is a network, then this looks like just like a large network with this, where this portion of the network is shared across all inputs. And so it's a shared parameter network. You could train this model, and in the process, you could train this projection matrix P as well. That clear to everybody? Everybody clear with this? Okay, so got a couple of yeses. Now, if I were using a time delay neural network, then you would say that every word is going to be, you're going to say every word is going to be predicted on the past few words. So here I have a fourth order predictor. To predict each word, I look at the previous 4 words. That's a time delay neural network. Except now, every word is going to be processed by this projection matrix P before it's fed to the network, to the hidden layer, which then predicts the next word. And the hidden layer typically in these cases would have a tanh activation. And the output is a softmax to predict the next word. But then you can have other kinds of models like this guy, where to predict any word, you look at a bunch of words both preceding it and succeeding it. So this is called the soft bag of words predictor. You predict a word based on the words in the immediate context, again, as before. To predict the next word, each of these words is first projected using the P matrix, and then you predict the center word here. And backpropagation propagates the error back, so you also learn P. Or this is a skipgram, where you use a word to predict all of its neighbors. Once again, you have a projection matrix P, and the projected down word is used to predict all of the neighbors. And then again, you can use backpropagation to train this guy. And if you do all of this properly, it turns out that in some cases, you can end at the down projected words actually capture semantic relationships. So Thomas Mikollov had this lovely paper in 2013 where he showed this, where he used this to learn low dimensional projections of words. In this case, he used a 1,000-dimensional model. And then here he's showing a PCA down to 2 dimensions of these 1,000-dimensional representations. But you see something very interesting. This is the 1,000-dimensional vector for China. This is the 1,000-dimensional vector for Beijing. This arrow represents the difference between Beijing and China. Similarly, this arrow represents the difference between Russia and Moscow, Japan and Tokyo, Turkey and Ankara, Poland and Warsaw. What do we see over here? You see a pattern? Ron, this would be used for both training and inference. Every time the word is always going to be projected down. So do you guys see a pattern over here? what we find is that China minus Beijing is approximately equal to, say, Poland versus minus Warsaw, right? So in general, country minus capital seems to be the same for every country. So these vectors which link up words seem to capture semantic relationship. In their paper, they also show how man minus woman plus king, or woman minus man plus king gives you queen, right? Things like that. Beautiful. And so that leads us to our first poem. Yeah, wrong. This is Birtbeck. Okay, 15 seconds, guys. Okay, let me end this poll. What's the answer to the first one? Is the first statement true? Second one, true or false? Third, fourth. Is the fourth one is false, right? You cannot, because if you want to add one more word, you have to add an entire new dimension regardless. So only the first three statements are true. The distance between any two non-identical one-hot vectors is the same. Words are represented using one-hot embeddings because they don't impose any a priori assumption on which words are closer than others. And word embeddings derived from language models are lower dimensional real value representations, where the distance between words is a meaningful representation of their closeness. The projected down one hot vector is called a word embedding. So let's use that. I'm going to, anytime I represent words at the input, you're going to have to assume that there's a projection matrix that projects it to the embedding, right? And so now if I'm modeling language with recurrence, I'm always trying to predict PT, WT, given all the previous words. Now here, if I just use a finite number of previous words, you end up with a TDNN. But what we really wanted to do was to predict each word given every other word that occurred before it. And for that, we need a recurrent network. And so you'd have a recurrent network of this kind, where at each time, you're trying to predict the next word. Now observe that you don't need an explicit training output and a training input. The input itself is the output. To train this model, you would give word sequences, and at each time as you're training the model, the next word that is going to be input is also going to be the target output. And so you get the target output from the input itself, because the output is simply the input shifted by 1. At time 3, the target output is W4. At time 4, the target output is W5, and so on. And now you can just use back propagation through time to learn this network. And in the process, you can also learn peak. Is this making sense? This model? I have 1 yes. What about the rest of you guys? 2? Can you give me a 4 yeses? 2 more yeses? Okay. I guess I'll have to be satisfied with it. Thank you. And so now, once I train the model, if I want to use it to generate new stuff, how would I do it? I could just give this model a short string of words, like, fourscore and then the model is going to, at each time, the model doesn't output a single word. It actually outputs a probability distribution over all the words in the vocabulary. And from this distribution, I will draw a word, W4. And so if I'm using it in generative mode, I'm only given W1 through W3. After W3, it computes the probability distribution for the fourth word, from which I'd sample the fourth word and then feed it in at the next time. And at the next time, it's going to give you the probability distribution for the fifth word. from which I sample the next word and keep doing this on and on and on, right? Is this making sense? What we just did? Okay. So how would we know when to stop? If you're modeling, if this is a good model for the language, it must model sentences. Sentences come to an end. How would this model know when to stop? Anybody? You need an end of sentence marker, right? So, by the way, so these, if you have something like this, like programming, you don't need an explicit end of sentence marker. Here, you always know when you're done. Why? Because if the first curly brace closes, the program is over, right? But more generally, you're not going to have a situation like this where there's a natural end of termination. There's a natural indication of when things are terminated. So, and if you don't have that, then you're going to end up with something like this. I don't know if you can hear this. This was trained on MIDI files from piano, and if you put it in generation mode, it keeps generating music forever. So here, if you're always feeding the drawn word as the next word in the series and draw the next word by sampling from the output distribution and keep feeding it, we need to know when to stop. And for that, we identify an issue. First, a sequence of words by itself does not indicate if it's a complete sentence or not. For example, if you just saw this word sequence 4 score and 8, can you tell me, just by looking at this, if it's the beginning of a sentence, the first 4 words of a sentence, or the last 4 words of a sentence, or somewhere in the middle? Just by looking at this, can you tell me if its position in the sentence? You really can't, right? You need to make this explicit. And so we have explicit markers which indicate the beginning of a sentence. We have an explicit marker to indicate the end of a sentence. So the SOS is the start of sentence, EOS is end of sentence. And so if I just say 4 score and 8, it has neither an SOS nor an EOS. So this is clearly the middle of a sentence. On the other hand, if I have this SOS marker, which is start of sentence marker 4 score and 8, it means that these guys are the first 4 words of the sentence. This is just a marker, but it's part of your vocabulary. So the start of sentence 4 score and 8 means these are the first 4 words of a sentence. 4 score and 8 end of sentence means after 8, the sentence ended. This one, SOS 4 score and 8 EOS, means that this is a full sentence. Is this making sense to all of you? I'd like to see 50 yeses because this matters. Okay. Keep going so I know, okay, I think you get it, right? So thank you. Now, very often we won't have an explicit start of sentence marker. We may use the same symbol for both start of sentence and end of sentence, or just dispense with it because it's implicit. But in the most generic case, you expect to have a start of sentence and an end of sentence. And we'll assume that in our lecture. So how does synthesis happen? You keep drawing a word and feeding it in until you draw an end of sentence marker. When you draw an end of sentence marker, you know the sentence is done. That's when you stop. So the story so far, language models model the probability of a word or symbol sequences in the language. This is typically performed in the form of next symbol prediction. Given a symbol sequence, it computes the probability distribution of the next symbol, given everything so far. And this can be computed using a recurrent network. And once you train an LM, it can be used both to compute the probability of a given symbol sequence or to generate or extend symbol sequence given an initial set of words or prompt. So, any questions so far? Did all of this make sense? Just give me a yes, thumbs up, and I know. Okay. And so you have your second poll. This was quick. Okay, 10 seconds, guys. I think we got everybody. Okay. Oh, not bad. So, which is the answer? Okay. Thank you. What is the strange picture of the corner? You're going to have to tell me at the end of the lecture, guys. Keep your eyes peeled, okay? And so we've spoken about language modeling. Let's return to our problem. Our problem was sequence to sequence modeling. Sequence goes in and a sequence comes out. How does this relate to language modeling? In language modeling, what we modeled was P of y1 through yn, right? In a sequence to sequence model, we are still learning a language model, except we are learning a conditional language model. We are modeling P of y1 through yn given x1 through xn. Is this making sense? This one? The difference between simple language modeling and sequence to sequence conversion? Okay. So assuming that I'm just using a recurrent neural network for my language model, right? Where at each time you produce an output and this guy goes back at the next time. This was how we modeled this guy, right? How would you model this guy? Anybody? You understand how this came from here, right? Yes or no? So how would I model this? Any thoughts? This is the same as this guy, right? The only difference is that now you're also giving it this guy as an input. These two problems are the same. What this means is that I need some process that takes x1 through xn, derives some representation from it, and feeds it in as a conditioning input. And once this is fed in, then the whole thing just becomes this guy. Is it making sense? Yes or no? Right. Very simple, right? You didn't change a whole lot. All that happened is that your conditioning, actually, which is the input, now becomes an additional input to your language model. And that's what we're going to be talking about. Again, we've already handled this guy. We're looking at sequence to sequence models where there's no correspondence between the input and the output. But in this case, what we are realizing is that this is just a standard language model, except now it's conditioned on the input. And so the input must somehow be fed to the language model for it to use it effectively when it generates word sequences. Okay, any questions? Any questions? Okay, if not, let me continue. So for that, we're going to use some variants of this model. And can you see how this model actually satisfies the thing that I just said, or almost satisfies? This would be our input. It's producing something, and that something is going into the decoder, right? So here's how it looks. There's a first block which processes the input to generate a hidden representation from it. This is what I'm calling the delayed sequence to sequence. And then the second block, here's the pseudocode. You're going through time, and at each time you're computing the recurrent hidden state based on the recurrent hidden state of the previous time and the current input. And the final representation is what you get when the final symbol has been input. And using our notation, this should be an EOS. Okay? This clear? What we just did? Okay. And then subsequently, this guy is going to take this one and keep generating the outputs. For this, doing it in just this manner is kind of naive. Why is that? So here's what you would be doing, right? You've gone through the input, you produce the hidden state at the final time. Then on the right-hand side, on the generation side, at each time, you're computing a recurrent hidden state, which is based only on the recurrent hidden state at the previous time. And from this recurrent hidden state, you are drawing you're computing a probability distribution, which is the YT. You're computing both the recurrent hidden state and the output probability distribution, and from that, you're sampling the word. You keep doing this. But this is kind of naive, right? So this guy is, the output at each time is a probability distribution of symbols, YT. We are drawing a word from this distribution, as we saw. But here, each word that is output depends only on the hidden state and not on the previous word. So why is that a problem? Think of a machine translation case, right? So let's say I get a probability distribution over here, and the probability distribution assigns equal probabilities to the word A and the word an, which can happen, right? So I could choose either A or an out here. If I choose A, then can this word be eagle? If I choose A over here, can this word be eagle? Yes or no? No, right? If I chose an, can this word be table? Also no, right? But then, is there any way for this model to know that I actually chose an A out here in this model? Does this have the ability to know that A was chosen and so it should not make table impossible? That information is not there, right? Do you see that? Yes or no? Okay, so how do you fix this? Feed in the output, right? Exactly. And so this, because this, this is just restating it. So you're going to feed this guy right back. It's a self-referencing or an auto-regressive sequence to sequence. It's auto-regressive because it's regressing on its own outputs. And so how does this work? This is what we call the simple translation model. First, this block processes the input. So if you had I ate an apple, if you're performing machine translation, then this recurrent block is going to process the entire output until it encounters EOS. And the hidden representation when it encounters the end of sequence is the final representation for the entire input. Then this guy is going to take this representation as input and as the initial state, and it's going to take a start of sentence marker. You need the SOS. At the very first time, this is going to be an SOS. And then afterwards, it's going to just recurrently generate outputs as we saw before. So here's what it would do. At the very first time, it's going to take this guy, and it's going to take an SOS. There's an output distribution from which you draw the word, maybe ish. And then at the next time the ish goes in, you draw the next word. And you keep doing this till you get an end of sentence marker. So is this process clear? And is the role of SOS clear over here? This process clear? And the role of SOS, start of sentence marker, is also very clear, right? Very easy. Nothing fancy. And observe that because things are going back in here, if I drew a different word over here, I would have a different word over here, which means all the subsequent outputs are going to change. And of course, in my model, I just assume there's just a single layer hidden state. That hidden state can be arbitrarily complex. This is just for illustration purposes, so this is the picture I will use. But in your mind, you must know that the hidden state can be anything. It can be as complex as you want it to be. Okay. So here's pseudocode, how this works. First, you process the input and generate the hidden state at the final time. Then you process the output. And at each time, you work on the previous recurrent state and the word that you generated at the previous time, because that is now going back in. And you get a new probability distribution Y from which you sample the next word. And you keep doing this till you have obtained an end of sentence marker. So this process clear to everybody? Yes? Okay. And now, again, drawing a different word out here will mean there's a different word going in here. So all the subsequent outputs are going to change. And so this is our simple translation model. The portion of the model that processes the input is going to be called the encoder. The portion of the model that uses the final representation derived by the encoder and generates the output is called the decoder. But more generally, I want you to think of the encoder as the portion of the model that processes x1 through xn and gives you some representation. And the decoder is actually a language model which generates y1 through yk, ym, and it's conditioned on this guy, which is actually representing this guy. And so it's the decoder is actually a language model, but it's a conditional language model. This making sense to everybody? Yes or no? So the encoder is deriving a representation from the condition, in our case text, and the decoder is a language model, but it's a conditioned language model. It's generating text conditioned on the input, conditional text, right? So here, this is self-reference, right? The answer is Shah. So it's autoregressive. Every word output over here, so okay. All right. And so, again, although I'm drawing things like this, I want you to remember that there's always a projection matrix which compresses these words are one-hot representations, tokens are one-hot representations. They must be compressed to a lower dimensionality. We do that through these projection matrices. If I'm doing something like a dialogue system where the input is English and the output is also English, the projection matrix could be the same for both sides. If I'm performing machine translation going from English to German, this P1 and this P2 could be different. P1 is the P1 for English, P2 is the projection matrix for German. So there are different ways of setting this up. Now, what does the network actually produce? At each time, the network is, remember, this is a conditioned language model, right? So at each time, the network is actually producing a probability distribution over all the output vocabulary, conditioned on all the previous outputs and the input. So at this time, it's actually, at the first time, it's just producing probability of, y1 given y0. Y0 is, you always have to start with the next start of sentence marker, right? And x1 through xn. That's what it's producing at this time. This making sense? Okay. And then at the next time, you draw a word from it, you feed it back. And what do you think the output is going to be now? What will the output be? Output be here. Anybody? What is it going to be? Anyone? What will it? Can someone tell me? Y-apfel? No. It's going to be the probability distribution for y2 given SOS and ish and x1 through xn, right? This making sense to everyone? Yes or no, right? Yeah. And so that's what you'll get over here. And from that, you're going to draw the next word because you're sampling. And that goes back in. And what will the output now be? Just to build on the same thing, just to test if you got it. What is the output here going to be? Anyone? What will it be? What is this output here? Come on, guys. This is going to be P of y3 given SOS ich habe and I ate an apple, right? So you get it. Beautiful, guys. Make my job easy. And so you get a probability distribution from which you draw the next word, and you keep doing this until you eventually generate an end of sentence marker and you're done, right? So observe that at each time, you're actually outputting a probability distribution, which means that if I choose a word from here, say harbor, that had a probability. That is going to be y1 harbor out here, right? And so if I want to find the probability of this word sequence is simply the product of the probabilities of wherever the einen, right? Abfell, gegessen, and the end of sentence marker. It's going to be the product of the probabilities of the words that were chosen. That making sense? We're just using Bayes' rule to compute the probability of this, right? So it's very simple. And now, if I'm actually performing machine translation, what do I want to do? Again, as a reminder, at each time, the network outputs a probability distribution over the words, given the entire input and the entire output sequence so far. At each time, a word is drawn from this distribution and it's provided as input at the next time. And this continues till the end of sentence marker is met. So the actual generation process is going to look like this. At each time, you are outputting a probability distribution from which you're drawing a word which goes back in, right? And you keep doing this till you get this end of sentence marker. And now this question is, what is this business of drawing the word? I choose a word and the word had some probability, but how did I choose this word? What is this magic operation of drawing from y of t? Now, of course, you could just do a random draw, right? But that's not what you really want to do. Remember that the probability of any word sequence in the output conditioned on the input is simply going to be the probability of the first word conditioned on the input times the probability of the second word conditioned on the first word in the input, and so on all the way to the end. This guy is simply y of O1. This guy, which is the probability of the second word, is y2 of O2. The next one is going to be y3 of O3. This last one is going to be yl of OL. And so the probability of this word sequence, the symbol sequence conditioned on this input, is going to be this product. Is this making sense to everybody? Yes, no? Right. So that's easy. But then, which word sequence do you really want given this? Which word sequence do you really want as the output if you're performing machine translation? Do you want to draw any odd word sequence, or does it have a characteristic in your mind? The most probable word sequence, right? You always want to get the most probable word sequence. So again, here, if I want to get, I can get a probability for any odd word sequence. If I want a probability for ich weiß nicht, was es soll bedeuten given I eat an apple, then I can break it down as, probability of ich, weiß given ich, nicht given ich and weiß. I've not indicated the start of sentence marker, but you're going to have to assume that it's present till I generate the end of sentence marker. But what I really need is not any odd sequence. I want to produce the most likely output that ends in an EOS. So I want to get the O1 through OL such that the sequence, the product of their probabilities, is the maximum possible. This clear to everybody? Okay, how could I possibly do this? Could I just pick the most likely word over here, stick it in, then pick the most likely word here, stick it in, then pick the most likely word and stick it in? And will that give me the most likely word sequence overall? What do you think? No. So why not? Why not? Okay, let's see an example of one. Okay. So that's greedy. What we just saw is greedy, right? Select the most probable word at each time. And that's not obviously the best thing to do, right? So in the greedy thing, this draw could just be an argmax, and that's going to give you the word, but it's not satisfactory. And why is it not satisfactory? Because if you just pick the most likely symbol at any time, this may cause the distribution to be more confused in future, whereas choosing a less likely word currently could cause the distribution at the next time to be more peaky, resulting in a more likely output overall. So let me give you an example. So let's say I'm performing something like speech recognition. The encoder is processing speech. The decoder is generating word sequences conditioned on the input. And so let's say that at some time, the first word was he. And then for the next word, the word knows with KN or WS, and the word knows have very similar probabilities, but knows has a somewhat slightly higher probability. If you acted greedy, knows has a lower probability than knows, so you would choose knows, and so you stick knows over here. But then he knows, this is the nose with the object on your face. Is this a, can you think of any ways of any of how you can extend this word sequence? Is there any, are there any plausible extensions of this word sequence? He knows, right? It's confusing. It doesn't look like a sentence or the big part, any part of a sentence. So when you get to the next word, the model is going to be very confused. It's going to assign, let's distribute the probability of all words. And so all of the words will have very low probability. So regardless of what you pick, the sequence of 3 words is going to have a low probability because these guys have low probability. On the other hand, if you had chosen knows, even though it had a lower probability, now he knows is actually a structured sentence. So maybe the word something has a high probability, right? Or he knows me, the word me has a high probability, right? And so what happens is that because the conditioning is so nice and strong, these guys will have a high probability. And then if you pick one of these out here, by the time you get to 3 words, this sequence is going to have a much higher probability than this one, although the second word by itself had a lower probability than the one here. This making sense? Yes, no? What about the rest of you guys? Any questions? I see some 6 yeses. So either the rest of you lost me, or I lost you, or I don't know. Okay, let me try again. Did you get this? Just give me a yes. Okay. Thank you. So why would nose have a then knows? Remember, if you're doing any kind of translation, if you're recognizing speech, then the input speech is going to have all kinds of noise. So, and nose and knows are pronounced pretty much the same, right? So these 2 guys are pronounced almost the same. And pretty much exactly pronounced exactly the same. And so completely arbitrarily, then they're not going to have the exact same probability. It's very unlikely, given that you're working with real numbers. And so it's very likely that this guy is going to have the higher probability. Did that answer your question, Shubhay? Right. And so this would happen, right? And I'm giving you a trivial example, but this happens all the time, right? And so, but then a priori, you don't know which word you should have chosen. How do you know? I mean, here I have a nice semantically meaningful example, but that's not always going to happen. And so, which word should you have chosen? There's no way for you to know because you have no way of knowing what can follow, right? So, you can't have any way of knowing how this will influence the future. So, to give you another example, suppose you've gone all the way back here, and here, let's say the word he and thee had very similar probabilities, but he had the higher probability because maybe you mistook the in the D to be maybe some noise, like a click, right? And so this had the slightly higher probability than this guy. But if you had chosen the instead, even though the had a lower probability, then the word nose over here would have been just fine. And the nose can actually give you a third probability, which and then you can extend it such that this 3-word sequence has an even higher probability than the 2 sequences that you just saw. But for this, you had to be able to look 2 words into the future. This making sense? What I just saw, what I just explained? Right. And so you don't know how far out your choices are going to come back and bite you. And so this is a problem, right? So how do we deal with this? It's impossible to know a priori which word leads to the more promising future. Choosing the lower probability the instead of he over here might have made nose more reasonable, right? So in general, making a poor choice at any time commits us to a poor future, but we cannot know at that time that the choice was poor. So how do we fix this? Instead of trying to be greedy, we can just say I'm going to randomly sample a word at each time according to this output probability distribution. And surprisingly, this actually works kind of works. But it's not really, it's very, very unlikely to give you the most probable outcome. You're going to get some random outcome, although it may be better than greedy. So here, if you were just doing random sampling, you just randomly sample from y of t, from the output distribution. But unfortunately, this is not guaranteed to give you the most likely output, although it could sometimes be better than the greedy outcome. So what can we do instead? For what? Before that, let's answer this point. Here's your third one. There are 3 questions. Okay, 15 seconds, guys. Shrikant, don't worry about it. They will keep track. All right, let me end this poll. Okay. So first question, true or false? Second one. Last one. I didn't actually tell you how you're going to sample from a distribution. I assume that as computer science students, you know how to do this, right? Or even if you're not, this is something that's standard. We can just write a piece of code for it. So here's where we have making a poor choice at any time commits us to a poor future, but you cannot know at that time that the choice was poor. So what is the solution? Don't choose. What do I mean? So let's say the encoder has done its thing. Then the first symbol is, definitely SOS. So I can pass this start of sequence marker and the hidden representation over here. This is unambiguous. And then you get a probability distribution. But then this probability distribution is over all the words. I take every one of these words and feed them as input. So I make as many copies of the decoder as there are words in my vocabulary. And so I, one for every word. And then this guys, each of these is in turn going to be a probability distribution. And so then I make as many copies again for each one of these as the vocabulary and feed each of these words in. And I keep doing this, and eventually I'm going to get an end of sentence. I can keep tracking the probability of the end of sentence markers. And I'm explicitly enumerating every possible word sequence. And this enables me to pick the most likely word sequence. What could be the problem with this approach? Is this theoretically correct first? Yes or no? Is this theoretically correct? But is this feasible? So how would you solve it? You guys are smart. You know how to solve it. Beam search, right? So what do? At the very first time, you get a probability distribution. You keep a beam. You just pick the top k. Only those top k are fed in. Say in my example, the top 2, right? And then you get an output distribution. But now, at each point, you're not looking at the local probability. You're looking at the probability of the word here, which is he, and the word here. You're looking at the product. And so you're going to get, word pairs, right? So you're going to get, like, if the vocabulary size is V, you're going to get V products over here. You're going to get V products over here. So you'd have 2 V terms. And from those 2 V terms, you're going to select the top K, the top 2. This makes sense? That you're actually multiplying the probabilities and not just looking at the local probability, right? Clear to everybody? And so then you're left with, say, only 2 overall. And then those 2 again can be, will generate probability distributions, each of them. Here my beam size is 2. And now how many terms must I multiply to get the actual scores of one of these candidates in this set over here? How many terms would I be multiplying to get the actual scores of each of these 2B candidates? Anybody? Over here, I'd have to multiply the probability of he, the probability of no's given by this guy, and this term. So here I'd actually be multiplying 3 probabilities for each one of these candidates. This would be the, maybe no's, and 3 probabilities for each of these candidates. And so each candidate is now a multiplication of 3 terms because each of them is the third word in the sequence. And those are what you're comparing to take the top K. Is that making sense? Right. And so you'd continue doing that until eventually at some point, at each point, you're always multiplying the probabilities along the entire path to pick the top K. And eventually one of them is going to hit an end of sentence marker. You're always going to get an end of sentence marker, but then you're going to get one where the sequence of probabilities terminating in the end of sentence marker is the highest. That's when you're going to generate an output. Or if you're really interested in generating the top K, hypotheses, this guy stops, but others can be continued. And so you can keep continuing till you come out with your top K guesses or top N guesses. So this making sense so far? Yes? Okay. All right, very easy. And so I have pseudocode for beam search. I'm going to skip that. We'll get to our last one. Okay, 10 seconds, guys. Okay, I'll end this here. And first statement, true or false? Second one, true or false? Is the second true? Is beam search theoretically correct? You want to represent every possible word sequence, right? Beam search is throwing away a whole bunch of candidates. So there's no guarantee that this actually gets you the most likely word sequence. It's definitely going to be much better than greedy, but it's still not theoretically correct. And in computer science terms, this is inadmissible. But it's practical, so we do it. The correct thing to do is to consider every possible thing, but that's infeasible. So you're given a choice between infeasible and inadmissible. We choose the inadmissible. Well, what we mean by inadmissible is that it's not theoretically correct. It's just an engineering solution. So this is the answer. Questions so far? Any questions? Okay, if not, let's go to the next topic, right? This whole thing will work. So what if there are 2 parts? He knows, while the other one he knows. The probability the second one is higher usually. Not necessarily, right? Just because it's shorter doesn't mean it's going to be going to have the higher probability. But yes, in practice, we end up having to perform some hacks, some tweaks to adjust for the fact that there is a bias towards shorter sentences. That's a good question, Shul. Any other questions? So we add things like length penalties and so on. So far so good. We've understood everything, right? The main question, how do you train the system? I must learn to make predictions appropriately. Given I ate an apple, it should produce Ishaba and an apfel guessing. So training is like everything else. Forward pass, I input the scores, but then here is the crazy thing. Here, I'm actually also inputting, I'm training this like I'm training a language model. This is different from how I train regular neural networks. Do you see the difference? In a regular neural network, an input goes in, you get an output, and you compute a loss. In this setting, you just give it, I ate an apple, and then this would generate some arbitrary sentence. Your target sentence would be Ich habe, blah, blah, blah. You'd compare this to this guy, you'd get a divergence, and you train your network. That's how you train your regular network. Yes or no? Right. What's different over here? What's different over here? Here, in addition to the input, you're also feeding the target output, Ich habe. Right? Yes or no? So this is not the correct way to train a neural network, is it? It's cheating in some sense because you're feeding the target output in. You will never have the target output at inference time. Remember, in training, the forward pass must mimic inference time. At inference time, you don't know the truth. Everything is randomly generated. Whereas here, you know the exact truth. You know the first three words must be Ich habe einen, right? So that's different. You see the difference over here. Right? Do you see the difference? Right. So it's a bit of a cheat, but why do we do this? If I did this the correct way, then the output could be in the beginnings, could be garbage. It could just be yes, 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 yes. How do I even compute a divergence between a random sequence of words and a target sequence of words, which is Ich habe einen Apfel gegessen? It's not possible. And so we use this cheat in order to reduce it to a situation where we know that we are familiar with, where there's a one-to-one correspondence between each output and the target output. And once you reduce it to a state where there's a one-to-one correspondence, we know how to write losses and we can train the network. So, make sense to everybody? Yes or no? Yeah. So again, I want you to remember this is what they call teacher force. You're giving it the answer, partial answer, and it's outputting the next answer. In reality, you wouldn't, during inference, you won't have a partial answer to produce the next word. So once you do that, then this is like training a language model. You're going to have the target output at each time, which is always the next word. And then you can compute your divergence. You can backpropagate the divergence all the way to the beginning, to the network, to learn the net, and then train the network. In practice, if you're using stochastic gradient descent, you wouldn't use all of them. What they would do is just randomly choose one of these words and propagate derivatives only from that one to go back to the input. So the overall training mechanism is something like this. You're given several training instances, input and desired output. For each in the forward pass, you compute the output for x and d, except that now you're both using both x and d in the forward pass. This is different from your classical training paradigm. Then in the backward pass, you compute the divergence between the desired output and the actual output, except in the manner that you train language models, and then propagate derivatives for updates. So again, this is a sequence to sequence model. Sequence goes in, sequence comes out, right? And there are many applications like machine translation. You could teach it to say that, when somebody says, my name is Tom, then it can come out with Ich heiße Tom, or my name is Tom. That's translation, right? Or if you're doing speech recognition, the speech recording goes in, you get an embedding, a sequence of embeddings. The output could be my name is Tom. Or a dialogue system, I have a problem, and the answer is how may I help you? Or an image to text, where the encoder actually encodes a picture, and the output text is the caption for the picture. All of these are different applications of this simple model. Now, for this to work, this hidden representation that you get at when the final input has been processed, this is what is being passed to the decoder. So clearly this must represent the meaning in the sentence. Does it actually do it? So in the original paper that introduced this work by Sutskever et al., they show these beautiful examples. Here are three sentences. John admires Mary. John is in love with Mary. John respects Mary. All three have a similar sentiment, but not identical, and they're arranged like so, right? This way. Then change the person, subject and object. Mary admires John. Mary's in love with John. Mary respects John. And they have roughly the same arrangement as these three guys. Moreover, this vector, John admires Mary, Mary admires John, looks very much like this vector. John is in love with Mary, Mary's in love with John. And it looks just like, very similar to this guy. John respects Mary, Mary respects John. Here's another example. Changing the manner in which it's said, active versus passive. I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden. She was given a card by me in the garden. In the garden, I gave her a card. I gave her a card in the garden. And you can see that the arrangements are very similar. So it actually turns out that it learns a pretty good representation, semantic representation of the word sequence out here, if you train the model on enough data. Is this making sense to you guys? This example of what happened here? Right. There's two of you. Okay. I don't know about you, but the first time I read this, I found this to be very impressive. And so here are some examples of machine translation. This is in French. I have no way of knowing if this is right or wrong, but so there's a machine translation example, Ulrich Hakenberg, membre du Conseil. I'm not going to try to pronounce it. And here's what the model comes out with. It's very, very correct, so I'm told, right? Here's one which I can understand. This was used for a dialogue system where they're trying to replace a human in the help desk. Machine, what is the error that you're running, please? I'm seeing an error related to VPN. And the machine comes back as, what is the error message that you're getting when connecting to VPN using Network Connect, connection refused or something like that? May I know the version of Network Connect to connect? So this is one wrong word. I'm not sure I know that. Is the Network Connect prompting for any user certificate? This looks so very plausible. This could be a human, right? It's doing a surprisingly good job. And so this model really works, really, really works. And you can also do the same, use the same thing for image captioning, except that in the encoder is now going to be a convolutional neural network, which generates an output, which is fed to this decoder, which is a conditional language model, except now it's conditioned on the image, and it generates outputs, and you can train it just as before. Here are some examples that it produces. So the input is processed with a CNN, and you generate your output, and you can train it, right? So the very first exam paper on image captioning used this technique. And this was the first paper on image captioning. This is more than almost 10 years old at this point. And it's remarkably good for the time, right? Man in black shirt is playing a guitar. Construction worker in orange safety vest is working on a road. Two young girls are playing the Lego top. Yeah, I mean, she's not a young girl, but still, right? Boy is doing a backflip on a wakeboard. And even the mistakes are not totally absurd. A young boy is holding a baseball bat. This I never got. A horse is standing in the middle of the road. I don't see a horse. But still, right? Pretty impressive, given the simplicity of the model and what it was actually trained on. And of course, you can have variance. Remember, this is just a conditioning input, right? So there's no reason for the conditioning input to only go in to the very first term. It could be fed in at every time. So do you see how this is different from the model we saw earlier and why this makes sense? Right. Same thing over here, image captioning. It's only a conditioning input on the language model. It could go in at every time, right? So these are simple variants that people came up with. And they make sense once you realize it's a conditioned language model. Here was one where they were trying to generate video descriptions, where a CNN is run across all the frames, you pull them, and that's fed into the decoder at every time to generate outputs. So anyway, pseudocode. I'll skip that. So the story so far, language models model the probability of the word or of word or symbol sequences in the language, typically through next symbol prediction. The simple sequence-to-sequence model that we just saw for tasks such as machine translation are performed using an encoder-decoder model. The encoder extracts feature representations for the input symbol sequence. The decoder is a conditional language model that uses this representation to conditionally generate the output symbol sequence. An inference is performed to find the most probable output sequence given the input sequence. And the same mechanism can be used for other conditional generation tasks like image captioning, video captioning, etc. So great. But then we have a problem. The problem is that the representation of the input is entirely imposed on this guy, this one thing. And if the input is long or complex, this poor guy gets overloaded and has to work very hard. And he very often will fail to do so. So how can we improve on that? We'll address that in the next class. We're done with today's lecture. So any questions?
Professor,
Yeah.
can you explain why feeding the input sequence in reverse helps?
Why feeding the input sequence in reverse helps? Simply because typically the first word over here is more related to the first word out here, right? And getting the initial portion right is crucial to getting the rest of it right. Whereas if I feed the input sequence in the forward order, by the time I get here, the information about the word I is highly diluted. Remember, in a recurrent network, there's always a recency bias. That answer your question?
Yes, thank you.
Yeah. Any other questions?